preparing for an EV test engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you create a validation test plan for an EV powertrain system? I start by mapping system requirements to measurable test cases, then split validation into battery, inverter, motor, charger, thermal, and vehicle-level tests. For each case, I define inputs, operating range, instrumentation, pass-fail limits, and safety precautions. I include normal operation, edge cases, derating, faults, and recovery behavior. Finally, I maintain traceability in a requirements tool and automate repeatable tests where possible. A good plan proves both performance and safe behavior. While answering, focus on requirements analysis, test coverage, boundary conditions, pass-fail criteria, traceability, safety controls, instrumentation, and how you separate component, subsystem, vehicle level, and regression testing. Question 2. What key tests would you perform to validate a battery management system? For a BMS, I validate measurement accuracy first, cell voltage, pack current, and temperature against calibrated references. Then, I test SOC, SOH, cell balancing, charge limits, discharge limits, contactor sequencing, isolation monitoring. Fault tests are critical: overvoltage, undervoltage, overcurrent, overtemperature, sensor open or short, and communication loss. I also verify CAN messages, diagnostic trouble codes, and recovery behavior. The goal is not just accuracy, but safe, predictable protection. Make sure to cover voltage, current, temperature sensing accuracy, SOC, and SOH estimation, cell balancing, contactor control, fault detection, protection thresholds, communication, calibration, and abuse or boundary condition testing. Question 3. How do you test CAN communication and diagnostics in an EV? CAN testing checks whether ECUs exchange the right information at the right time. I verify message IDs, cycle times, signal scaling, byte order, counters, checksums, and DBC consistency using tools like CANO, Canalizer, or similar loggers. For diagnostics, I test UDS services such as reading DTCs, clearing faults, session control, and data identifiers. I also inject missing, delayed, or corrupted frames to confirm fallback behavior. Timing and robustness matter as much as payload correctness. In your answer, talk about CAN frames, message timing, signal scaling, DBC validation, bus load, UDS diagnostics, DTCs, fault injection, logging tools, and handling missing or corrupted messages. Question 4. What safety checks are required before working on a high-voltage EV system? High-voltage safety starts before touching the vehicle. I confirm training authorization, wear rated PPE, follow lockout-tagout, remove the service disconnect if applicable, and wait for DC link capacitors to discharge. Then I verify absence of voltage using a properly rated meter, testing the meter before and after. I use insulated tools and avoid working alone. If the test requires energized operation, I define exclusion zones, emergency shutdown, and clear communication with the team. Be sure to mention PPE, lockout-tagout, service disconnects, voltage verification, insulation checks, discharge time, one-hand rule, trained personnel, emergency procedures, and compliance with company safety standards. Question 5. What is HIL testing, and why is it important for EV validation? HIL, or hardware-in-the-loop testing, lets me test a real ECU against simulated vehicle components. For EVs, the model may emulate battery cells, motor speed, inverter response, charger behavior, temperature sensors, and faults. It is valuable because dangerous or rare scenarios can be tested repeatedly without risking hardware or people. I use it for regression, diagnostics, timing, and fault handling. HIL does not replace vehicle testing, but it catches software and integration issues much earlier. While answering, cover real ECU testing with simulated plant models, battery and motor emulation, fault injection, repeatability, early validation, safety benefits, automation, and limitations versus vehicle testing. Question 6. How would you validate EV charging behavior for AC and DC fast charging? Charging validation covers communication, power transfer, safety, and user behavior. For AC charging, I verify pilot signal interpretation, current limits, connector lock, ground fault response, and onboard charger performance. For DC fast charging, I test handshake, insulation checks, precharge, requested voltage and current, ramp rates, thermal derating, stop conditions, and charger interoperability. I log BMS, charger, and vehicle messages together. The key is proving the vehicle charges safely across stations, temperatures, and battery states. Make sure to cover charging standards, pilot communication, handshake sequence, current limits, voltage limits, thermal derating, connector locking, fault handling, interoperability, logging, and end-of-charge behavior. Question 7. What tests would you perform on a traction inverter and motor drive system? A traction inverter test focuses on controlled torque delivery and protection. I validate torque command tracking, speed range, current limits, efficiency maps, DC bus behavior, phase current balance, and regen operation on a dynamometer. I also check resolver or encoder feedback, thermal rise, derating, short circuit protection, overvoltage, undervoltage, and overtemperature response. Noise and vibration can reveal calibration or control issues. I always correlate electrical data with mechanical output, because smooth torque is what the driver actually feels. In your answer, discuss torque response efficiency, current ripple, switching behavior, thermal performance, protection features, resolver or encoder feedback, regenerative operation, derating, NVH, and fault response. Question 8. How do you validate the thermal management system of an EV battery pack? Battery thermal validation proves the pack stays within safe and efficient limits. I test at hot, cold, and transient conditions using chamber tests, road tests, and fast charge profiles. I monitor cell temperatures, coolant inlet and outlet temperatures, flow rate, pump behavior, fan commands, and temperature spread across modules. I verify derating when limits are approached and check sensor plausibility. A strong result is not just low peak temperature, but controlled gradients and repeatable behavior. Be sure to mention temperature sensor validation, coolant flow, heat rejection, cell temperature spread, fast charging, cold start, derating, thermal runaway prevention, environmental chamber testing, and data correlation. Question 9. How would you test regenerative braking performance in an EV? Regenerative braking testing checks energy recovery without compromising stability or pedal feel. I evaluate regen torque across speed, SOC, battery temperature, drive modes, and deceleration requests. Then I verify blending with friction brakes, especially during ABS, ESC events, low traction surfaces, and near zero speed. If the battery is full or cold, regen must reduce smoothly and predictably. I compare commanded torque, actual torque, brake pressure, vehicle deceleration, and driver feel. Smooth transitions are the real success metric. While answering, focus on torque blending, battery charge limits, SOC and temperature dependency, brake pedal feel, ABS or ESC interaction, deceleration targets, drivability, energy recovery, and safety fallbacks. Question 10. How does ISO 2626 influence EV test engineering? ISO 2626 changes testing from simple feature verification to safety argument building. After hazard analysis defines ASIL levels and safety goals, I test whether safety mechanisms detect faults and move the system to a safe state. Examples include contactor faults, torque command errors, sensor failures, and communication loss. I keep traceability from safety requirements to test results, including fault injection evidence. The mindset is clear. Prove the system fails safely, not just works normally. Make sure to cover functional safety lifecycle, hazard analysis, ASIL, safety goals, verification methods, fault injection, safety mechanisms, requirements traceability, confirmation measures, and evidence documentation. Question 11. What is the difference between DV and PV testing in EV programs? DV, or design validation, proves the engineering design meets requirements using prototype or engineering intent parts. PV, or production validation, proves manufacturing intent parts and processes can repeatedly deliver the same performance. In an EV program, DV may focus on battery performance, inverter limits, thermal capacity, and software behavior. PV adds production variability, durability, compliance, and reliability confidence. I treat DV as proving the design can work, and PV as proving it can be built consistently. In your answer, explain design validation versus production validation, prototype maturity, engineering intent, manufacturing intent, sample sizes, durability, compliance, reliability, and how results guide release decisions. Question 12. How would you approach EMI and EMC testing for EV components? EVs create serious EMI challenges because inverters, DC-DC converters, and chargers switch high voltage at high frequency. I test conducted emissions, radiated emissions, and immunity according to relevant automotive standards. If a failure appears, I look at grounding, shielding, connector bonding, cable routing, filter design, and switching patterns. I also monitor CAN and sensor signals during immunity tests. EMC is not only about passing a chamber test, it protects communication, diagnostics, and vehicle reliability. Be sure to mention conducted and radiated emissions, immunity, high-voltage switching noise, grounding, shielding, cable routing, test standards, failure diagnosis, mitigation techniques, and impact on communication networks. Question 13. During a road test, the EV unexpectedly reduces power. How would you debug it? First, I make the situation safe and capture the exact operating conditions: speed, grade, SOC, temperature, drive mode, and driver input. Then I review logs for DTCs, torque request versus delivered torque, battery current limits, inverter temperature, motor temperature, DC bus voltage, and CAN communication health. Power reduction is often intentional derating, not a random failure. I reproduce the issue under controlled conditions, isolate the limiting ECU, and confirm the root cause with targeted tests. While answering, cover safe stopping, log collection, DTC review, battery limits, thermal derating, inverter faults, pedal and torque requests, CAN timing, reproduction steps, and structured root cause analysis. Question 14. What tools and automation practices would you use for EV test data analysis? For EV testing, I rely on clean data pipelines. I collect synchronized CAN, analog, temperature, GPS, and power analyzer data using vehicle loggers and lab equipment. Then I process it with Python, MATLAB, or dedicated tools to validate limits, timing, energy consumption, and fault behavior automatically. I like generating repeatable reports with pass-fail criteria rather than manually scanning plots. Automation saves time, but signal naming, time alignment, and calibration accuracy must be controlled carefully. Make sure to discuss data loggers, CAN tools, calibration software, Python or MATLAB analysis, automated reports, signal validation, synchronization, anomaly detection, dashboards, and repeatable regression workflows. Question 15. How would you test fault handling for contactors and precharge in a high-voltage system? Precharge prevents a large inrush current when connecting the battery to the inverter DC link. I test the sequence: negative contactor, precharge path, DC link voltage ramp, main positive contactor, then precharge release. I verify timing, voltage thresholds, and current behavior. Fault cases include precharge timeout, contactor stuck open, welded contactor, unexpected voltage, and insulation fault. The system should block readiness, set diagnostics, and discharge safely. This test is critical because contactor errors directly affect high-voltage safety. In your answer, talk about precharge purpose, DC link voltage ramp, contactor sequencing, weld detection, timeout faults, insulation checks, current monitoring, safe shutdown, diagnostics, and fault injection methods. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.